Hello, everyone. I'm Professor Harrison, and welcome back to our module on probability for finance. Today, we're going to be covering conditional probability and independence, two of the most important ideas in all of probability theory, and the ones that end up being the most misunderstood in practice. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to his family fortune. Today, he's starting to ask whether the problems he's facing are connected to each other, or whether they arrived independently. He opens another one of those mysterious letters. The probabilities we defined in the first two videos were unconditional. They described how likely something was before any other information came in. But information arrives constantly, and when it does, probabilities change. Conditional probability is the formal way to update a probability when you learn something new. The conditional probability of event A given event B is written P of A given event B, with a vertical bar in between them. The formula is probability of A given B equals probability of A intersect B divided by probability of B. In plain English, this says of all the scenarios where B happens, what fraction of those also have A happening? You're restricting your attention to a smaller world, the world where you already know that B is true, and asking how likely A is within that world. For example, instead of asking how likely a stock is to rise in general, you're asking how likely it is to rise specifically in a recession year. For example, consider a stock. If A has an unconditional probability of 50% that it ends up rising, then what is the probability that it ends up rising given that we know that it's a recession? Suppose historical data shows that the probability of recession in any given year is 20%. The probability that a stock rises and a recession occurs in the same year is 5%. What is the probability that the stock rises given that we know that it's a recession year? Well, we can calculate this. The probability of a stock going up given a recession equals the probability that the stock goes up and the recession happen together divided by the probability of the recession. That's the 0.05 divided by zero point 0.2, which equals 0.25. So around a 1 in 4 chance that the stock goes up given that we know that it's a recession year. So even in a recession, the stock rises a quarter of the time. Maybe it's in a defensive sector or something. The conditional probability tells us it's something that the unconditional probability couldn't. It accounts for the fact that we know the economic environment that the stock is actually in. So if we were to say that there's a 50% chance that the stock rises, that wouldn't necessarily be true if we know that there's already a recession. Instead, there's only a 25% chance that the stock goes up. Notice that we needed the joint probability of both events to compute this. That's where the multiplication rule actually comes from. If you rearrange the conditional probability formula, you get that the probability of A and B both happening equals the probability of B times the probability of A given B. What this means is that the probability that two things both happen equals the probability of the first multiplied by the probability of the second, given that the first already occurred. For example, the probability of a recession and a stock rising is the probability of a recession times the probability that the stock rises given that there is a recession. The next thing that I want to cover is the law of total probability. This comes up when the sample space can be divided into a set of mutually exclusive and exhaustive events, meaning that they don't overlap and together they cover every possibility. Now, if we want to find the unconditional probability of some event, then we can take each possible state of the world, find the probability that your event occurs within that state, weight it by how likely that state is, and sum everything up. What this means is that you're asking how likely is this event overall, and you can do that by averaging across every possible environment that it could occur in, weighted by how likely it is that that environment ends up happening. For example, to find the overall probability a borrower defaults, you'd average the default probability across boom, normal, and recession scenarios, weighted by how likely the default is within each of those scenarios. Here's that example worked out in full. A bank wants to know the unconditional probability that a borrower defaults. The economy can be in one of three states: a boom state, normal state, or a recession state, and each has its own default probability. In the boom state, we have a probability of 30% that the boom state occurs, and given that it's a boom state, there's a default around 1% of the time. In a normal state, which happens with a probability of 50%, a default can end up happening around 3% of the time. In a recession, with a probability of 20%, we have a default probability of 10%, given that things are not going so well. So overall, if we wanted to find the probability that there ends up being a default, We would just multiply each of these probabilities that the states occur times the conditional probabilities that the default happens within each of those states. So we'd multiply the 1% chance of defaulting given that we're in a boom state times the 30% chance that a boom state happens. We'd multiply the 3% chance of defaulting given that we're in a normal state times the 50% chance that a normal state occurs, and so on. Then when we add all those up, we get that the unconditional chance that a default ends up happening is around 3.8%. Here, we have effectively calculated the unconditional probability that a default ends up happening using the conditional probabilities of defaulting in all of the possible states of the world. That's what the law of total probability allows us to do. Go from a series of conditional probabilities to an unconditional probability. Next, let's talk about Bayes' theorem. Conditional probability gives you the probability of A given B, but often you know it the other way around. You know the probability of B given A, and you want to flip it. For example, we might know how likely an earnings miss is if a company is heading towards default. But what we actually want is the reverse. Now that we've seen that the earnings have missed, how likely is the company going to default? Bayes' theorem gives us that flip. The formula says your updated probability of A given B equals how well B fits within A being true, scaled by your prior belief in A, divided by how likely B was overall. The three pieces have names. The initial probability of A before seeing any evidence is called the prior. The probability of the evidence given A is true is called the likelihood. The updated probability of A seeing the evidence is called the posterior. Bayes' theorem is just the mechanical process of turning a prior into a posterior using the likelihood. Here's the earnings miss example worked out. An analyst initially assesses the probability that a bond defaults within a year at 5%. The company announces an earnings miss, and historical data shows that 60% of bonds that eventually default had an earnings miss beforehand. 15% of those bonds that don't default also had an earnings miss. What is the updated default probability now that we know that the company has had an earnings miss? The numerator is the likelihood times the prior, 0.6 times 0.05, which is 0.03. For the denominator, we need the total probability of seeing an earnings miss, whether or not the bond defaults. That is 0.6 times 0.05 plus 0.15 times 0.95, which equals 0.1725. The posterior is 0.03 divided by 0.1725, which is approximately 0.174. So what we found is that the default probability jumps from 5% up to 17.4% on the back of one piece of bad news. We'll note that there's a common mistake with Bayes' theorem worth naming directly. The probability of A given B and the probability of B given A are not the same thing, and they can often be very different numbers. The probability of a stock crashing in a recession is relatively high, but the probability of being in a recession given that one stock has crashed is going to be much lower. Stocks can crash for a whole lot of reasons that have nothing to do with the broader economy. Always remember that the thing after the bar is what you already know, and the thing before the bar is what you're trying to figure out. The two are different questions. So now let's talk about the special case where new information doesn't change anything. We define two events as being independent if knowing that one occurred tells you nothing about whether the other occurred. We can formally test this by multiplying the individual probabilities of each event. If that product equals the probability of both events happening together, then they're independent. If it doesn't, they're not. What this means is if two events are independent, the probability of both happening is exactly what you'd expect from multiplying their individual probabilities together. Knowing one happened gives you zero new information about the other. For example, if you know that it rained in Tokyo, that does not tell you anything about whether a particular stock in New York actually went up. Those two events are going to be independent, so the probabilities of both of those things happening at the same time is just the product of the two unconditional probabilities. Equivalently, independence means that the conditional probability equals the unconditional probability. The probability of A given B is just the probability of A. B is irrelevant. Take two assets in the same portfolio. Asset 1 has a 60% probability of rising, and asset 2 has a 55% probability of rising. Historical data shows both rise together 30% of the time. Are they independent? If they were independent, you'd expect them both to rise 0.6 times 0.55, which is 33% of the time. But they only rise 30% of the time. Those aren't equal, so the two assets must not be independent. If they move together slightly less often than independence would predict, which means they're mildly negatively correlated, That ends up being useful from a diversification standpoint, which is why we need to keep track of these things in the world of finance. The whole logic of diversification rests on this. If all stocks were truly independent, you could eliminate almost all risk by holding enough of them. In reality, stocks within the same sector tend to be positively correlated. Stocks across sectors tend to be less so, and during market crashes, correlations spike, which is the worst possible time for diversification to break down. Understanding independence is how you understand when diversification works and when it doesn't. Danny puts the letter down. He notices something strange about the letter's contents. It's dated nearly 20 years ago and it references specific positions in Victor's hedge fund that it knew by name, information that an outside investor should not have had access to. Brushing these suspicions aside, he notices that he's been treating the estate proceedings and his personal debt as two separate problems, but they're not independent. The estate is nearly empty because Victor lost his money over decades. Danny accumulated gambling debts because he assumed the estate would cover them. Danny's debt is conditional on what he expected from the estate. So the probability of Danny's debt being unmanageable given the estate is intact is very different from the probability of Danny's debt being unmanageable given that the estate is gone. He pulls out a piece of paper and starts working on the two problems side by side. He finds that the probability of being able to clear his debt is very much so different, conditional on whether or not the estate ends up being cleared. Specifically, if the estate ends up not being cleared, then there's a very high chance that he will not be able to clear his gambling debts, which is not reassuring. So that's conditional probability and independence. Conditional probability lets you update your probability when you learn something new. It restricts your attention to a subset of the sample space and asks what's likely within that subset. Bayes' theorem gives you the tool to reverse the conditioning when you know the probability in one direction, but you need to go in the other. Independence is the special case where the conditioning doesn't matter at all. And all of these rules end up being derived directly from the three axioms that we started this introduction to probability with.